Hey everybody, and welcome back to the Falkenblick Skills Center, where we build confidence with skills and we build skills with training. Let's talk a bit today about the Universal Transverse Mercator Grid System, or UTMs. There's a lot of theory and reasoning that we could get into when talking about UTMs. But I'm not going to lie, and unless you're this guy, you're probably not interested in all of that. Now, I've always been the kind of student that needs to understand the why behind the how in order for me to feel like I learned something. And that fact tends to shine through in my teaching style. I know that can make for a long lesson in many cases, and your time is valuable, so I'm going to try to leave out a lot of what is happening behind the curtain, so to speak, and focus today mainly on what you need to understand in order to pull and plot a UTM grid coordinate on a map. The Universal Transverse Mercator is a type of projection used to flatten our three-dimensional Earth onto a two-dimensional sheet of paper. Take a look at this beach ball. You see the shape of each of those colored sections? Well, in cartography, that shape is referred to as a gore, and it's this shape that forms the basis for the entire UTM system. If you were to cut each of those colored shapes out separately, they could be laid flat on a surface to form a two-dimensional image like this. With the flattened image, we can superimpose a grid that can be used to plot location and measure distance and direction with near perfect accuracy. The UTM grid consists of 60 north-south running zones, as they're called, each of which is numbered from 1 to 60, starting at the international dateline and counting up towards the east. These 60 zones are each 6 degrees of longitude wide and cover latitudes from 80 degrees south to 84 degrees north. Each zone is bisected with a north-south running central meridian. This central meridian forms the midline of a metric grid that covers the zone. All 60 zones have a central meridian with an assigned value of 500,000 meters. This central meridian is one of the grid lines, but is coincidentally an actual line of longitude as well, which is why it's referred to as the central meridian. The central meridian is the only grid line in the zone that points not only to grid north, but true north as well. All other north-south lines within the zone begin to diverge from true north more and more the further away they are, either east or west, from the central meridian. The grid laid over the zone actually extends beyond the eastern and western edges a bit, which is why you will never see a UTM grid with a zero easting. The smallest and largest grid eastings can be found along the equator, where the width of the zone is the widest. The smallest easting at the westernmost edge of the 6-degree zone is roughly 166,000 meters east, and the largest at the easternmost edge is around 834,000 meters east. Northings are measured in the southern hemisphere, counting down from 10 million at the equator to around 1,110,400 meters at the zone's southernmost limit. In the northern hemisphere, they are counted from 0 at the equator to around 9,334,080 meters at the zone's northernmost limit. So, it's entirely possible to have a northing number in the southern hemisphere that is identical to one in the northern hemisphere. This fact is why it is necessary when communicating a formal UTM grid to provide the hemisphere designation, either north or south, directly after the zone number. For example, 32N, or north, which tells the person using the grid that it is located in the northern hemisphere of zone 32. Now, if you're ex-military, you may have already realized that since the easting must contain 6 digits and the northing could have as many as 8, it's entirely possible to have an unbalanced grid coordinate. What I mean by that is, unlike the Military Grid Reference System, or MGRS, which always needs to have the same number of digits in the easting as the northing, UTMs do not. For example, the town of Nanyuki in Kenya can be found with the UTM grid 37 north, 285,242 meters east, and 0000820 meters north. So the sanity check that all grids need to be balanced or contain an even number of digits doesn't hold true with UTMs. In my opinion, this is one of the downsides when compared to grid reference systems, since depending on how a grid is written or otherwise communicated, it can introduce the possibility for error. We will get into this a bit more in a moment, but first I want to talk a bit more about the UTM grid system and the US Military Grid Reference System. Now, this video is not meant to teach you the MGRS, but I do want to mention something that you will likely come across if you are browsing other videos on UTM grids. Many people, like me, who were introduced to coordinate systems in the US military, more than likely learned the lat-long system and the MGRS. The MGRS was created in the 1940s and based squarely on the already existing UTM grid system. I'll save the details for another video. Just know that when the MGRS was created, it introduced the idea of additional east-west running bands that further divide the 6-degree wide north to south zone that forms the basis of the UTM system. There are a few reasons why these bands were introduced, one of which was to be able to abbreviate the lengthy numeric UTM strings. The MGRS is a great system, my favorite actually, but the fact is it's not so easy to find printed maps as a civilian with MGRS already overlaid. More than likely, the topos that are readily available to civilians include only the UTM grid information. But since the two systems are so similar, it's no big deal to learn one if you already know the other. The issues arise as soon as you realize that many digital devices such as smartphones, GPSs, don't do a good job of truly differentiating between the two formats. Remember that with traditional UTMs, you only need to know the grid zone and the hemisphere, either north or south, to be able to accurately plot a grid. Band identifiers, which are really a part of grid reference systems, are not required. Likewise, for communicating a UTM to another person, all that is needed is the grid zone designator and either N or S, depending on whether the grid falls north or south of the equator. In many cases, I'd even venture to say in most cases, people claiming to send a UTM grid will include a band identifier instead of a hemisphere identifier, which means if you receive a UTM such as 16S, 442562 560 6520, there's no way of really knowing for sure, without a follow-up question at least, whether you should plot it in the southern hemisphere of the grid zone number 16 or in the Sierra S band located in the northern hemisphere of that same zone. This happens because, as you can see here on this map, the UTM grid zone designator is listed as 32 uniform, with the U representing an east-west band. Strictly speaking, if we were communicating a traditional UTM coordinate, we would be more interested in the fact that the map lies north of the equator. The reality is that modern maps, GPS units, smartphones, and mapping software often blend elements of both the UTM and grid reference systems. Most of the time, this causes no problems at all, but occasionally it can introduce confusion when coordinates are exchanged between users who are expecting different formats. Let's keep this fact in mind as we move forward with the lesson, and I'll give you a few tips later on how you can minimize the likelihood of error. Now that you understand that the Earth is divided into these 60 zones and each zone is overlaid with a metric grid, let's take a closer look at just how that grid is broken down. As we mentioned earlier, the central meridian of each of these grids is drawn at 500,000 meters east, which means the grid which overlays the zone is 1,000,000 meters wide and actually extends a bit left and right of each of the geographic zones. The widest part of the geographic zone lies, of course, along the equator. The width of the zone there extends from approximately 166,022 meters east to 833,978 meters east, which means at the equator, the overlaid grid actually extends beyond the eastern and western edges of the zone by about 166 kilometers on each side. As you can see, as you move north or south away from the equator, less and less of the grid is actually used, until at the northern end of the 84-degree north latitude, the zone is only a bit over 70 kilometers wide, so about 35 kilometers left and right of the central meridian. And at the farthest south end, at the 80-degree south latitude, it's a bit over 116 kilometers wide, or around 58 kilometers left and right of the central meridian. Let's pivot now away from the theory and towards practicality. The fact is, the first place you'll be interacting with this UTM grid system is probably when you see it overlaid on a map. Depending on the scale of your map, the grid squares printed on it may represent 1,000 meters each, or in the case of some small scale maps like 1 to 250,000s, they more than likely represent 10,000 meters each. But for land navigation purposes, I'm going to assume you're either using a 1 to 24, 1 to 25, or if you're really unlucky, a 1 to 50,000 scale map. But in either case, the UTM grids will be spaced at 1,000 meter intervals. Now let's get into how we can use this grid to express our location on Earth. Let's start out by working from big to small, or another way to say it would be from less precise to more precise. How precise depends on what you're doing with that information. If you ask me where I live, Germany may be all you need to know. But if you want to mail me a package, you're going to need a different level of precision if you expect it to ever arrive. If your mother calls and asks where you are, telling her you're camping in Yellowstone National Park is probably enough. If she wants to hike out and roast marshmallows with you, she's going to need a more precise location. This is simply how location works. The amount of precision we need depends on the task at hand. A general location may be sufficient for casual conversation, while other situations may require much greater precision. The goal isn't to always be as precise as possible. The goal is to be precise enough to successfully accomplish the task. As we work through the grid system, you'll see that each additional digit further refines your location, allowing you to describe your position with greater and greater detail when the situation demands it. Take a look at this excerpt from a 1 to 25,000 topographic map in Germany. In the lower left-hand corner of the margin, we find a section commonly referred to as the grid note. The grid note contains information related to the map datum, the type of coordinate system, and the elevation datum. It's also where you will find the grid zone designator if it's using the UTM system. In our case, the GZD is shown to be 32, and a band identifier is also indicated as U, or uniform. In our case, this map supports the use of UTMs, lat longs, and another common grid system often used in Germany, known as Gauss-Krüger. The information shown under each section is an example of what the information referring to each particular system should look like on the map. For example, you can see that the Gauss-Krüger information will be shown as light blue on the face of the map, while the UTM-related annotations are in black. Now imagine that you and a friend are talking on the phone, and each of you have the same map laid out in front of you. You're looking for a nice campsite to spend the weekend at, and after a minute or two, you notice this hilltop marked here with the spot elevation 560. Because your friend and you are working with the same map, you can simply pass him a 4-digit grid to the 1,000 meter square that the hill is in. The grid zone designator in this case is not so important since the both of you already know where you are within the 32 zone. When pulling or plotting coordinates on a map, the rule is always read right and then up. In other words, the easting comes first, then the northing. Take a look at the way the grid line running north to south just to the left of our point is annotated. It's labeled 442E. Can you see that the last two digits are larger than the first one? These are known as the principal digits. They indicate the beginning of the next 1,000 meter square. When taken together, however, they indicate that the 4-2 grid line actually lies 442,000 meters or 442 kilometers east in grid zone 32. Now let's get the northing so that we can get our friend's eyes on our hilltop. Look for the grid line that runs east to west just below our point. In the left margin, we can see that it is marked 5606N, and you know now that the last two larger digits are the principal digits, which indicate the next 1,000 meter square. When taken together, though, we can see that the grid line actually lies 5,606,000 meters or 5,606 kilometers north of the equator. And the next grid line north, labeled 07, is actually 5,607 meters north, or 5,607 kilometers north. The principal digits represent the number of thousands. So when you see the number 5606, you need to see it as 5,606,000. Using our right and up rule, we would ask our friend to look in the 4206 grid box to find the hilltop 560. And for this application, a 4-digit grid coordinate with no grid zone designator is sufficient. This 4-digit grid identifies 1,000 by 1,000 meter square, and since there is only one hilltop labeled 560 in this square, further precision is not necessary. So our friend approves of this location and then asks where we should park and walk in from. For this, we need to further refine the precision of our grid since there are many small streets and intersections within this grid box. Let's pick one that we want to use as our parking spot. This looks like a good place here. Let's now refine our previous 4-digit grid so that our friend will know where to meet us. As you can see, these 1,000 meter squares are not broken down any further on the map. To plot within the 1,000 meter square, we need some kind of a map plotter. It's not really so important what style you choose, there are many, but it is important that it's scaled appropriately for your map. Trying to use a plotter scaled for a 1 to 24,000 map on this 1 to 25,000 will wind up being more frustrating than helpful when measuring distances or plotting grids, since things won't really line up accurately. If I overlay a grid of my own onto the 4206 square, you'll quickly see how easy it is to continue to refine our coordinates. Let's talk about coordinate precision. Any easting you pull from a location within one of the 60 zones will never have the need for more than 6 digits, since, as we mentioned earlier, even along the equator where the zone is the widest, the lowest easterly value at the far western edge of the zone is approximately 166,022 meters east. And the largest easterly value occurring at the far eastern edge of the zone is 833,978 meters, roughly. Okay, I know sometimes people will place a 0 at the beginning of the easting so that they can keep the digits balanced with the 7 digits in the northing, but that isn't necessary, and it won't change what I'm about to show you. In the previous scenario with our camping buddy, we were both looking at the same map, and we already knew our general location, so the formalities of the UTM system were not really important to us. But it is important to recognize and understand that there is a formal protocol for passing UTM coordinates. One of those protocols is to always pass the entire grid. So an Easting will always have 6 digits and a northing will always have 7. This fact reveals one of the turds in the UTM punch bowl, and that is that there's no clear method for expressing reduced precision as there is with the military grid reference system, for example. Take a look at this coordinate. 32N 567439 meters east, 57,06433 meters north. This coordinate refers to one specific square meter of real estate. Its precision can be said to be 1 meter. Now take a look at this coordinate. 32 November, 567000 meters east, 5706,000 meters north. Many people assume that because we replaced the last 3 digits with zeros, that somehow the coordinate represents a larger area. But that isn't actually what the coordinate says. This coordinate still identifies one specific square meter on the ground. The zeros are still digits. All we have done is move the location of the 1 meter square. Its precision is still 1 meter. The zeros are still digits that map to a specific location on the ground. Consider money for a moment. If I have $1,256,587 and I replace the last 6 digits with zeros, I don't suddenly have $1. The zeros still have value because they occupy a place in the number. UTM coordinates work the same way. As long as digits occupy those positions, they define specific locations on the ground. This reveals one of the fundamental limitations of the UTM system. Unlike the military grid reference system, there is no built-in way to communicate reduced precision simply by altering the coordinate itself. The coordinate always describes a specific 1 meter point, even when the sender intends to describe a larger area maybe. The only way to unambiguously communicate a reduced level of precision is to state it along with the grid when you communicate it to someone else. For example, you might say something like, location as follows: 32 north, 567439 meters east, 5706400 meters north, plus or minus 100 meters. This allows the coordinate to remain in proper UTM format while clearly communicating the intended level of uncertainty. Now let's get our plotter and refine the grid to our parking area for our camping trip. We already know the grid square, so we can start from there. Let's lay the plotter on the map so that the plotting triangle for the appropriate scale is laying like this, with the 0 at the bottom left of the square. Now, let's slide the plotter to the right until the intersection that we're interested in falls directly under the baseline of the vertical scale, here, while making sure that the horizontal baseline remains aligned with the 0,6 grid line here. Once we're happy with our alignment, we can read the Easting and add that to our coordinate. I see 780 meters east, but east of what? That's right, 780 meters east of the 4-2 grid line. So we can call our Easting 42780 meters east. And now the northing. I see that the intersection is about 620 meters north of the 0,6 grid line. So our northing becomes 0,6620 meters north. So we can now tell our friend that we should plan to park at the intersection located at 42780 meters east, 0,6620 meters north. Again, he doesn't need the grid zone designator or the numbers preceding the principal digits, since we know that we're both working from the same map. If, however, you wanted to contact a regulatory agency to ask for permission to camp in this location, you would need to pass a formal UTM by adding the grid zone designator and the entire coordinate string. It would look like this: 32N 442,780 meters east, 560,6620 meters north for the parking area, and 32N 442,260 meters east, 560,6220 meters north for the hilltop campsite. It turns out that the how of actually pulling the numbers from the map is pretty easy as long as you follow the right and up principle. But what about when someone sends you a UTM grid? How can you apply what you just learned about how to pull a UTM grid from your map to plotting a UTM grid on your map? The truth is, more than likely, the person you're exchanging grids with is already going to know what hemisphere you're in, and more often than not, they will be utilizing a map with a UTM grid on it as well. This makes things much simpler since, if that's the case, you can forego transmitting the grid zone designator, the hemisphere identifier, and even the digits that precede the principal digits can be ignored in most cases. You can simply pull and plot coordinates starting with the principal digits and refine your grid from there. For example, if I called my camp buddy and said, "Hey, pull out your Hairborn 1 to 25,000 topo," I've already set the stage to reduce the formalities, and I can just concentrate on passing 8-digit grids with 4 digits in the easting and 4 digits in the northing. Simple. My camp buddy tells me he thinks he's found a better place to camp and asks me to check out the spot at 46720955. Again, this is an abbreviated UTM that my friend and I are using because we have an understanding of what area of the Earth we're talking about. So let's take a look. First, a fact. No matter how informal you get, a grid should always at least begin with the principal digits. Meaning no matter if I receive a 4-digit grid, a 6-digit grid, an 8 or a 10-digit grid, I will always know that the first 2 numbers of the easting and the first 2 numbers of the northing will be the principal digits. If my friend passes me the grid 4609, the first 2 digits of the easting are 46 and the first 2 of the northing are 09. Therefore, I already know that this is only pointing me to 1,000 meters square. If he passes me 46720-09550, I can see from the 46 and the 09 that although this is a more refined coordinate, it still lies somewhere within the same 1,000 meters square. 4 digits in the grid get me to within 1,000 meters. 6 digits gets me to within 100 meters. 8 digits gets me to within 10 meters. And 10 digits, which isn't really possible to pull accurately from a 1 to 25, would get me to within a meter. Let's take his grid now and see what he's talking about. He passed me 46720955. Right away, I can put my finger in the 4609 grid square. Once I put my finger in this square, I see what I think he might be referring to, but to be sure, I need to get the plotter involved. The process is the same as pulling a grid, so let's begin by aligning the baseline of the plotter with the 09 grid line, like so. The vertical scale should be aligned on the 46 grid line here. Now, we can simply slide the plotter to the right or east by the amount after the primary digits. I see 72, so we can slide the plotter to the number 7, which stands for 700, and then to the first tick mark after the 7, which stands for 20. Together, we've slid the plotter 720 meters east of the 46 grid line. When that is aligned, we just need to locate the northing by looking up the scale by the amount listed after the principal digits. I see 55, which I know means 550 meters. Here's the 5, and now let's count the tick marks. Each one represents 20 meters, so here's 520, here's 540, and halfway to the next gets me to 550. Now, there may be cases where you need to plot a grid near the edge of the map, where you don't have a grid line to measure from. For example, here. If you wanted to pull the grid for this little structure here, you just need to remember that every grid square is 1,000 meters by 1,000 meters. So rather than lining up the baseline of your plotter on the line below the little structure, which is not drawn on the map, we would just lay the plotter on the map and measure from the 4-1 grid line to the structure, which gives us 640 meters east. So we can write our easting as 4164. Then we can align the 10 on our plotter scale with the 06 grid line above the structure, and we can see easily that the house is lined up with the 560 mark on our plotter. Since we know that the grid lines count up to the north, we just need to know that this last marked grid line here is 06, so the one below it must be 05. Therefore, our northing for this little structure is 0556 meters north. So the informal grid for this structure is 4164 meters east, 0556 meters north. The formal UTM grid for this little structure would be transmitted as 32 north, 441640 meters east, 5560 meters north, which in UTM language essentially means that this little structure lies 441,640 meters to the east of the western edge of grid zone 32 and 5,605,560 meters north of the equator. The UTM system has its flaws, that's for sure, but the principle behind it remains to be the basis for nearly every other grid reference system out there, with very minor differences which for the most part serve to improve upon its ease of use. I will make another video shortly on the US military grid reference system, which I personally find much easier to work with. It's much more intuitive, it requires less digits to be accurate, and it's structured in a way that allows the number of digits in the easting and the number in the northing to be balanced, which might not seem like much to hear me say it, but turns out to be a real help. If you're interested in catching that video, make sure to subscribe and ring the bell so that you'll know when I've released it. Okay, I hope your head isn't spinning too much. I tried my best to leave the most cerebral elements of the UTM system out, but I have to give you what I think you need to understand the why behind how you do things. Now, my advice for you is to find a map with UTMs drawn on it, get yourself a plotter or dig that one out of your old military gear and get to practicing. Because it's training like this that will help you build the skills you need to have the confidence when it matters. All right, I'll see you in the next one.